Okay, before we continue the discussion of the DNS signal structure, I have two comments. I just happened to look at the random variables class note and found that there's a mistake here. So we discussed that the power spectral density is given by the Fourier transform the autocorrelation function if this integral exists. Now this integral exists means this should be a infinity. It should be less than infinity. Okay, it was an error. Okay. So this denotes that the integral exists, and then only we can take the Fourier transform. Another comment is on class test 2. Many of you have referred to white noise as signal. Now, in this context, you should note that signal and noise are different as far as signal processing, estimation, and communication theory are concerned. Okay, you probably copied from the internet because I was just curious and I searched a little bit. I found that it was referred as signal, but noise and signal are different. Okay, we distinguish between noise and signal clearly in signal processing, estimation, and communication. So, as far as this class is concerned, signal means something that carries useful information, meaningful information, something that we want to track, estimate, something we want. Whereas noise just gets added as signal propagates through a medium or when it is received. Okay, so noise is something which is not desirable, which is not wanted. There is a clear distinction between signal and noise. And in GNSS, we talked about C over N, or carrier to noise power density ratio. There is a similar metric, equivalent metric called signal to noise ratio. We can also calculate signal to noise ratio in GNSS as the receiver processes the signal. Okay, and that clearly distinguishes between signal and noise. The higher the signal to noise ratio, the better is the signal quality environment. Okay, so do not refer to white noise as signal. You may have read it from some sources, but that is the downside of relying on the internet for everything, especially for technical information. Any question? Okay. Last time we talked about the GPS signal structure. We mentioned different codes and data, and also there are three different carrier signals. As far as this class is concerned, we'll stick to the basic structure, which is the quadruphase in the L1 band. Okay, so this is the notation that we are going to use for the signal transmitted by satellite I, where T is the time of transmission. So at this point, we are interested in representing the signal at the time of transmission. So in this representation, T is the time of transmission. And we are going to consider the most basic form of the signal structure in this class. Understanding signal structure is very important. If you do not follow what I am telling now, or in the next few classes, you will not be able to follow anything afterwards. We discussed that in each cardiac frequency there are two orthogonal components which are which are 90 degrees phase apart, in phase and quadrature phase. In phase is reserved for precise positioning service for authorized users, whereas quadrature phase is for civilian users. And in the quadrature phase, we are going to consider the most basic form, which is present in the L1 band from all satellites, in all satellites. So this is the L1 carrier frequency. Since we are considering quadrature phase of the L1 band, this is legacy nav data. We will talk a little bit about legacy nav data now. We already talked about the CA code. This is the power. The CA code this has a chipping rate of 1.023 megahertz. Each pulse is called a chip in case of the code, whereas in case of the navigation data D, each pulse is called a bit. The chipping rate is 1.023 megahertz, means there are 1.023 into 10 to the power 6 chips in a second, and the code period is 1 millisecond. It has a repetitive pattern which appears to be random over a short duration of time. That's why codes are also called pseudo-random codes. And they also have some, if you look at the pattern over a short duration, you will think that the sequence in which the plus minus 1 values are taken appear to be random. So the codes are also called pseudo-random noise codes. Okay. But there is a pattern which repeats every code period, and in case of CA code, the code period is 1 millisecond. So we say that the code is 1 millisecond long. Just to contrast this with the PCI's encrypted code, PY code or P code, simply P code, which is for the PPS, the authorized users, chipping rate is 10.23 megahertz for the PY code, and the code period is 1 week long. Okay, the PY code is 1 week long. So you just compare 1 millisecond versus 1 week. Okay, so this is the signal structure that we are going to follow in this class for all subsequent discussions of GPS. But we noted that there are other forms, there are other codes, that data, and they also modulate the carrier in different ways, but we will not consider them. And this kind of modulation where you just simply multiply code and data plus minus 1 values with the code and data with the carrier is called BPSK modulation. Okay, and we also looked at the modulated carrier in the last class. Okay, next we'll discuss a little bit about the legacy nav data, what it contains, how it is structured and all. So legacy nav data is basically 50 bits per second data stream. So here we have 50 beats per second, meaning each bit is 20 milliseconds long. You just divide 1 by 50 and you'll get the duration of each bit in case of the navigation data. So each bit is 20 milliseconds long. Okay, and a complete data set has 25 pages. Okay, each page has, so I'll go this way, each page has each page has 5 subframes. Okay, each subframe has 10 words. Okay, and each word has 30 bits. So from this structure we can find out the duration of word, subframe and pages. So 30 bits means each bit is 20 milliseconds long, and you need to multiply 20 with 30, 20 milliseconds, so that will be 0.02. So this will give 0.6 seconds. There are 10 words in a subframe, so 0.6 times 10 will give 6 seconds. And in a page there are 5 subframes, so 30 seconds. So one page gets over in 30 seconds, and there are 25 such pages, so 30 into 25 seconds, so that will be 12.5 minutes. So complete data set, navigation data set in case of legacy nav data requires 12.5 minutes. Okay. Now how the information is provided here. The first 3 subframes of all pages transmit satellite clock error from GNSS system time and ephemeris. Of the satellite. So each satellite will transmit its satellite clock error from GNSS system time and the ephemeris. The first subframe is reserved for satellite clock. First subframe satellite clock, and the next 2 subframes ephemeris. Okay, so all the pages have the same information in the first 3 subframes. Okay, satellite clock and ephemeris. So receiver requires at least this information. It requires satellite clock error. It also requires satellite position in orbit. We discussed that from ephemeris, which are orbital parameters, it is possible to determine the ECA position of the satellite in orbit. So this is bare minimum. Okay, the receiver requires this. Okay. Now it is not known when the receiver is turned on and starts processing. It is not known which subframe it will or which yes, which subframe it will receive first, right? So of these 5 subframes, 3 subframes have this information, but we do not know in what sequence the receiver will receive. So it can receive the 5th subframe first, then 4th, then 3rd. So that way 5th and then 1st, 2nd, 3rd, 4th. This way also it can receive 4th, then 5th, then 1st, 2nd, 3rd, 4th. So minimum of 30 seconds is required Okay, for the receiver to get this bare minimum information. Now, how about the fourth and fifth subframes? Okay, now they actually have different information in different pages. Okay, so the information includes the following: almanacs of all other operating satellites. I'm just giving you some example. Don't think that this only was is transmitted. There are many other pieces of information. We will not discuss them. Then ionospheric coefficients. I'll explain what these are. Okay, then this also includes PSV stands for space vehicle. Okay. Other satellite health. Then an important time called UTC. We are going to discuss UTC, what UTC, so don't worry about all this. Now, what are almanacs? Almanacs basically are orbital parameters. We talked about ephemeris. Ephemeris is more accurate than an almanac. Okay, these are also orbital parameters, but with degraded accuracy. See, accuracy is determined by how many bits you are reserving for transmitting a particular information. Okay, so more bits are allocated for transmitting ephemeris because the satellite needs to transmit its ephemeris with good accuracy. Whereas these almanacs are for other operational satellites. Okay, so they are transmitted in the fourth and fifth subgroup of the 25 pages with degraded accuracy. Now, why this is done? A receiver which has received signal from a particular satellite can decode the nav data and get this information. Okay, and using this information, although degraded accuracy, it can quickly find out which other satellites could be visible in the sky. Okay, so initially it takes time to determine which satellites are visible. So if it gets some prior information about the satellites, it can quickly find out which other satellites could be visible. Okay, and then ionospheric coefficients. Now we know that the ionospheric error is a dominant component of the pseudo range error, right? Later we'll see that using the dual frequency measurements, measurements with two carrier frequency measurements in two carrier frequency bands can allow us to eliminate the ionospheric error. Okay, so we say that with the help of dual frequency measurements, the ionospheric error can be eliminated. But what if this receiver does not have dual frequency capability? In that case, it has to proceed with single frequency measurements. Then what is the alternative? How can we eliminate the ionospheric error? With single frequency measurements, it is not possible to completely eliminate the ionospheric error, but we can have some models based on the physics of the ionosphere. Some models have been developed, and using those models, the user can partially remove the ionospheric area. The satellites transmit the coefficients of one such model, the basic model, okay, ionospheric model. Coefficients are transmitted in the navigation. Then health of other satellites, which other satellites are healthy, can also be obtained from these two subframes. Next is UTC. UTC stands for Coordinated Universal Time. It has replaced GMT now. Later we'll talk about this more. What is Coordinated Universal Time and why it is abbreviated as UTC, not CUT. Okay. So that's all about the legacy nav data, and I also told you what signal structure for GPS we are going to consider in this class. Any question up to this? Anything that you could not understand, ask me at this point. If you do not understand something, it will pile up and you will lose track. You will not be able to follow things. That's why I'm asking you repeatedly. Next, we are going to talk about the IRNSS signal structure. Again, for IRNSS, there are two types of services. SPS, Standard Positioning Service, which is an open service. Without encryption, no encryption. Okay, and then restricted service. This is only for authorized users. Okay, in this class we are not going to talk about the restricted service. We will only talk about the SPS, the Standard Positioning Service. Now, IRNSS transmits signals. The current satellites in orbit transmit signals in two bands. L5 and S. In case of L5 band, the center frequency, here I am giving all the frequencies that I have given are actually center frequencies, okay? 1176.45 megahertz, and for S band it is 2492.028 megahertz. Now future satellites will also transmit signals in the L1 band. Okay. I forgot one more thing in the previous class. If we go back and tell that. Here. So here we discussed why these bands are chosen for satellite navigation. One thing that I forgot to mention is that see the low frequency signals cannot penetrate the ionosphere. This is one drawback. Another drawback for low frequency signals is that you need a very large antenna to transmit signals. So antenna diameter has an inverse relationship with the frequency of transmission. Toward the frequency of transmission, higher should be the diameter of the antenna. And on satellites, we know that we cannot afford to have large antennas. We require small antennas. Okay, so this is another drawback of low frequency signals. So they require large antennas. I'll give you the SPS signal structure for IR analysis. So this is the signal transmitted by satellite I. Basically, it is the same as what we had written for GPS, but there are some differences, of course, in parameters. So this is the signal power. Signal power is different. In case of SPS, IRNS also uses CA code. The CA code that the GPS satellites use, of course, are not the same as those of IRNS satellites, but they have some similar properties and the same chipping rate, same code period, and generated by the same algorithms, but the codes are different. Okay. So there are certain algorithms that can only generate this pseudo-random codes. So the same chipping rate. So we are talking about the SPS structure only. So don't think that everything else is also the same as chipping. That's not. So this is nav data. We do not call it legacy nav data. Okay, so nav data. And this one is the carrier frequency. Already gave you the carrier frequency, the center frequency for L5 and S bands. Okay, let's quickly talk about the nav data, because the nav data structure is different. A complete data set is called a master frame. Okay, a master frame has 4 subframes. Each of 12 seconds. Okay, so a complete master frame gets over in 48 seconds. Okay, so there are 4 subframes, and each subframe has 16 synchronization bits followed by 584 symbols. Okay, Each symbol is 20 milliseconds long. Now, when the receiver decodes the NAV data, it takes this 584 symbols and converts it into 292 bits. Okay, and this actually contains important information. This 292 bits actually contains important information. Now, these 16 bits which appear in the beginning of each subframe are used to detect the subframe. Now, in case of GPS also, there are certain bit patterns in the beginning of a subframe and at the end of a subframe. Okay, yeah, the patterns are different in the beginning from that in the end. Okay, now using these specific patterns, it is possible to find out at what points the subframes have started. Okay, so in case of the GPS, we call preambles. Okay, this bit patterns in the beginning are called preambles. Okay, and then at the end there is another pattern which we call parity. Now, what the receiver does is it actually looks for the preamble to detect when the subframes have started. But it could also be possible that in the data such patterns are present. So to know whether it has correctly determined the beginning of a subframe, it also needs to check for parity, the bit pattern at the end. Okay, so preamble and parity are both together when matched will tell the receiver that a correct subframe has been determined. Beginning of the correct subframe has been determined. In case of IRNSS, there are different ways to determine the beginning of the subframe. So the 16-bit synchronization pattern is used. Okay, and also at the end of these 584 symbols, there is a certain number of bits which would always be 0. Okay, so using the synchronization bits and this n bit pattern, in case of IRNSS also, it is possible to find out when a subframe has begun. In case of I mean, basically the objective is to correctly determine the beginning and end of the subframe. Now, GPS does it in one way, IRNSS does the same thing in a different way. Okay. Now the navigation data is of two types. IRNSS navigation data is of two types. Primary navigation parameters, which are ephemeris, satellite clock error, from IRNSS system time. IRNSS has its own system time. Then there are other parameters also, I will not get into them. Then secondary map parameters are satellite almanac. Just like GPS, IRNSS satellites also transmit almanacs of other satellites. Then ionospheric coefficients, IRNSS time, offsets, from other GNSS system time on UTC. Then it also transmits some text messages. In a previous class, I told you that some IRNSS satellites are designated to broadcast short messages. So those messages are actually transmitted in the navigation data as secondary parameters. Okay. Don't think that these are only transmitted. There are other pieces of information as well, which we will not discuss here. So that's all about the IRNSS signal structure. Any question? Okay. Next, we are going to talk about UTC and GNSS time. Different constellations follow different time. Okay, GNSS time. We are going to talk about only GPS and IRNSS in this class. Okay. So let's start with UTC. As I noted earlier, UTC stands for Coordinated Universal Time. The time that we get now is actually UTC, not GMT anymore. Although synonymously we call it GMT, it is actually UTC. Okay, it has replaced GMT. Greenwich Mean Time. GMT stands for Greenwich Mean Time, so it has replaced the GMT. Now, how this time is derived? It's basically an artificial time. Okay, it is the weighted average of atomic times from so different countries have their national laboratories where they have precise atomic clocks. Okay, so using the atomic clocks, they derive time. These times are called atomic times. Now the UTC is derived as the weighted average. There are some sophisticated algorithms that the laboratories use. Okay, there is an international body that is responsible for maintaining this time, deriving this time. So they have sophisticated algorithms to derive the UTC using the weighted average of the atomic times of different national laboratories all over the world. Okay. Now this is an artificial time scale. Okay, we are using atomic clocks to derive a time, but we use UTC for daily activities. Okay, we time our activities, right? Daily day-to-day activities using a time which is artificially derived. So there has to be some mechanism to tie this time with natural phenomena. How is that done? It is kept within 0.9 seconds of UT1. Now we have come across another term, UT1. What is UT1? UT1 stands for universal time. Okay, this time is actually derived from Earth rotation rate. Okay, so it is tied to natural phenomenon, and we make sure that the UTC is within 0.9 seconds of UT1. I'll come to I'll tell you later how this is achieved. That the UTC is within 0.9 seconds of UT1. How this is achieved? Let's first talk about the UT1. Okay. To understand UT1, we first need to discuss UT0, UT0. This is actually mean solar time. UT1 is also mean solar time, but applying some corrections on UT0. So let's first talk about UT0, and then we'll see how UT1 is derived from UT0. So UT0 is the mean solar time. Okay. Now, how is this time derived? The time between two successive transits of a distant astronomical object. For example, quasars. So quasars are actually supermassive black holes. Okay? And they are extremely bright. Okay, we know that black holes engulf everything. It does not allow anything to go away, right? But it actually also has a disk of gases formed surrounding it. This disk transmits highly bright signals. Okay, so using that transmission, it is possible to identify supermassive black holes. Okay, and they can be distinctly identified in space. So the time between two successive transits of a distant astronomical object is recorded using an atomic clock at the prime meridian. Okay. Towards the beginning, we talked about the astronomical time, right? This is also done in a similar way, but here we use an atomic clock. At the prime meridian, only the time is recorded using an atomic clock. This time is called the sidereal time. Okay. So it's like there is an observer on that astronomical object, distant astronomical object. Okay, and as per that observer, what is the Earth rotation rate? How much time the Earth requires to complete one rotation about its axis? Right. That is what actually we are recording with an atomic clock on the Earth. They are equivalent, right? Time between two successive transits of that astronomical object is the same as what the observer sees at the time the Earth requires to complete one rotation about its spin axis. Both are the same. So basically what we are measuring with the atomic clock is nothing but the length of a day, and this is called a sidereal day. And we noted earlier that the length is 23 hours 59 minutes and 4.09 seconds. Okay, then this sidereal time is mathematically converted to mean solar time. Now you may ask why we did not use the sun to measure the time. So we cannot use the sun uh, to measure the time because the sun does not appear as a point. It appears as a disk, right? So which point of the disk will you take? The measurements will not be accurate. Okay. That's why we do not use solar observations to determine the length of a day. We use distant astronomical objects, distant stars, to find the sidereal time, and then that sidereal time is mathematically converted to the solar time. So what is mean solar time? Mean solar time is the average of the converted solar time based on multiple observations. So we find the sidereal times multiple times and then convert the sidereal times to solar time. So we get multiple solar times, and the mean of the all the converted solar times is the mean solar time. So this is mean solar time. This is UT naught. But because of the polar motion, if you record this time at different points along the 0° longitude, you will see different times. We know that the Earth's spin axis makes a circular motion with respect to the solid Earth, rest of the Earth. This is called the polar motion. Because of the polar motion, UT naught recorded at different points along the prime meridian is different. Now we do not want this. We want only one time, one universal time. UT1 is derived from the UT naught after correcting the polar motion. Okay, so UT1 does not have that problem. At any point along the 0° reference meridian, you will get the same UT1. The UTC is maintained within 0.9 seconds of UT1. How? By applying occasional lip second corrections. Okay. Now, before explaining how these corrections are applied, let me tell you why we call it UTC, not CUT. Basically, the International Telecommunication Union wanted to adopt an abbreviation for this time, which would be the same in all languages. Okay, they wanted only one abbreviation for this common time. But then the British proposed coordinated universal time, which would be abbreviated as CUT. And the French said something in French whose abbreviation would be TUC. Okay. Now, since different people are proposing different names, a compromise was reached with UTC. So, although we call it the Coordinated Universal Time, the abbreviation is UTC. Okay. Now, how we apply the leap second corrections? The leap second corrections are applied on 30th June and 31st December. Okay. So it can be applied once a year, twice a year. Some there are years where no leap second corrections were applied. Okay. The first correction was applied in 1972. The last one so far was in 2016. After 2016, till now, no corrections have been applied. Okay. The corrections can be positive or negative. Okay. Until 2021, it was observed that the earth is slowing down. Okay. And positive leap second corrections were applied. But in 2021, it was observed that earth is now rotating faster. But no leap seconds corrections have been applied in 2021. Okay. So till now, positive corrections have been applied, no negative corrections, because earth was slowing down all these days until 2021. So how the corrections are applied? If we have a positive correction, in that case, when the time is 23 hours 59 minutes 59 seconds, if you want to apply a positive leap second correction, positive leap second correction means you are actually slowing down UTC. UT1 is slowing down because earth was slowing down all these days. So you also need to slow down UTC. Okay. So by applying a positive correction, you can slow down UTC. So what they did after this time, instead of making 000 everywhere, they do this 23 hours 59 minutes 60 seconds. And after that only it will be reset to 0. So this is a positive leap second correction. How about negative leap second correction? In case of negative leaf second corrections, when the time is 59 minutes 58 seconds, at the next second we skip 59. We just make it 0. So 59 seconds is skipped. Okay. So this is how you can actually make UTC run fast. So you just remove 1 second and make it fast. Okay, now although the corrections have been applied till now, there are groups that oppose the lip second correction because this makes UTC a discontinuous time scale. Okay. At regular intervals, you have these jumps, and such discontinuities cause issues with software. Okay. The software manufacturers need to take care of UTC corrections well in advance. Otherwise, it would cause glitches. The software would not run properly. So there are groups that oppose lip second corrections, and currently a debate is going on at the International Telecommunication Union on whether this lip second correction should be abolished completely or not. No decision has been reached so far because there are people who actually support this lip second corrections, and there are groups that actually oppose. So currently, no decision has been reached, but after 2016, no correction was also applied. So that's all about the UTC. Tomorrow we will talk about GPS and IRNSS system time quickly, and then we'll talk about some important properties of the code. Okay, so these properties allow us to uniquely identify a satellite using the code, and understanding this is very important for all subsequent lectures. If you do not understand how the code is used to uniquely identify a satellite, many things that we will discuss later uh, will be difficult for you to understand. Okay, so that's it. Any question? Yes.
Ma'am, we are trying to run the software. We are able to gather the data from the application on the phone, but when I load it in the software, it says it has crashed.
I don't know. I told you not to do this at the last time. You probably have to reinstall it again and see. Or you can post a question on the forum.
Ma'am, the demo file works. The demo file that has been given with the software, they work and they generate the plots. But when we the data that we gathered, it
You can collect for a short duration and check. Do you have raw data? Have you collected raw data?
yes, I mean in the file when I open the file, it says that there is raw data is being collected. It has lines with raw and data.
Then probably how long is the duration of the data?
This one
How
I
long?
collected for 10 minutes.
No, reduce the duration and see whether it is working or not. Now, I cannot tell you why it is crashing for your data. So you have two options. Either you need to reduce the duration of the data, or you need to post a question on the forum and check what they say. The 10 minutes data should be handled by the software. I don't know why this is happening. You should actually stop all other applications. You should not run other applications when you're running the software. That could be
Ma'am,
an issue. There could be a
I did
memory
not
issue as well.
you repeat. I should stop all the.
Other applications running on the computer. So
Okay.
this is a problem specific to your laptop. Okay, so you need to see whether your computer is overloaded, memory is full, all those things you need to check. Okay, so you need to first check whether other applications are running. Then also if it crashes, then you need to reduce the duration of the data and see. And you can also post a question on the forum specific to your problem. So these are the
Okay.
some things you can do and see
Okay.
if it works or not.
And ma'am, in my area, there are a lot of buildings around. So can I instead gather the data on the terrace of my building itself?
You can gather it on the terrace. If you have an open space, you can always do that.
Okay, ma'am.
You need to find a suitable place. Okay. Uh,
Okay.
I gave you some guidelines. You just see whether you can follow that or not. I mean, to start with, it is better to collect data in an open space because for the first time you are doing, and if it does not work properly, um, you will not learn anything. That's why I told you to collect the first data set in an open space so that you get good quality measurements. Okay.
Okay, ma'am.
Any other question? Fine.
So, ma'am, once we are able to plot the data, we are supposed to present those plots and explain what we understand from those plots.
Yes, exactly. You should explain things. It should not be a mechanical explanation. Okay, you should try to analyze it to the extent possible based on what we discussed in the class and present your analysis. Like
Okay.
what kind of data you see, how many satellites, at what elevation, azimuth and elevation you see the satellites. What can you conclude about the measurements, about the clock, about the position estimates? Such things, the quality of measurements, such things should be explained in the
Okay.
presentation. Now, what kind
Uh,
of data you collected, duration of data, where you collected, what kind of signal reception environment you think it was. Things like this should be explained. Okay?
okay, ma'am. And how many data should we present?
One proper data set. Now, you can collect as many data sets as you want, but
Okay.
you should present results with one proper data set. It should not be too short or too lengthy. Okay, the data set, if your software cannot handle large data set, I don't know what the problem is specific to your computer. If it cannot handle long data sets, you can shorten the data duration and see whether that works. Because the demo data works, right? Did you see the duration of the demo data?
Yes, ma'am, the demo data works. I did not see the duration, but the file size is like 10 MBs, whereas my file size is 30 MBs.
Okay, 10 to 30 should not be an issue, actually. And here, I don't think there is anything time intensive, okay, computationally intensive operations are doing. It could be possible that you are running other applications and your memory is full. Something like that may have happened. Uh,
Ma'am, the this demo data, I think it says 1200 seconds, so maybe it's like 20 minutes.
Demo data, and your data is 30 minutes long.
10 minutes. It's 10 minutes long, but the file size is
10 minutes.
30 MB. The file size is three times larger.
That also depends on the phone, okay, the Genesis chip in the phone. But generally, raw measurements are logged once in a second. Uh, why it has more size, I'll not be able to tell you. But you can shorten the duration and see what is happening. If the demo data is 20 minutes long and it is working fine, this would not be an issue with your software or computer. You need to check what else may have gone wrong.
Okay, ma'am.
One thing that you can do is shorten the duration of the data and also make sure the computer is not running other application. Then you can post your question on the forum. Okay. Specific details should be given while posting the questions.
Okay, ma'am.
Any other question? Okay, fine. You can leave.
Thank you, ma'am.